All right, the second law of thermodynamics helps us to give us a better measure of efficiency. If you just apply the first law of efficiency, remember what I said of first law of efficiency. First law of efficiency basically says what you get out divided by what you put in. Okay? For a turbine, it's the burn something, so we call that QH, hot heat. Okay? So the efficiency of a turbine would be the work out divided by the QH in. Okay? And every device has its own efficiency. The problem with that first law of efficiency is that you don't really know if 40% is good or not, or 50% is good or not. In fact, if I had a turbine and I said, here's a 40% first law efficiency, you might be inclined to think that was bad. But in light of Carnot, that might actually be great. All right, that might be, Carnot might be 42% and you're at 40%. So you might think that's pretty darn good, right? So what we do is we have a new definition of efficiency that's in light of the second law. And the nice thing about these definitions of efficiency is that it makes more sense in terms of its numbers. If you say you're at 90% isentropic efficiency, that efficiency where 100% isentropic is going to be pretty much close to like a perfect device. Okay, so it's you have a lot better way of feeling out the numbers, okay, than you do with first law efficiency, with second law efficiency. Okay, sometimes we call these second law efficiencies or isentropic efficiency equations. Okay, so this is the last part of 7 that I think is pretty important. Let's take a look at a few of these isentropic efficiency equations. Now, again, no memorization here. Okay, you're going to get all these equations on an equation sheet. The thing is, I probably won't say turbines, compressors, pumps, nozzles. But what I will do is notice how each one of them has a little subscript, a little T, C, P, or N. All right, you'll have that. Okay, so you'll have something. Okay, but it's really the concept that's the most important thing. A turbine. What you're going to do is you're going to compare your turbine work generated to an isentropic turbine. We're going to assume isentropic's like the perfect turbine, the best turbine. You're going to take your turbine work and divide it by the isentropic turbine, because I'm going to assume the isentropic turbine is going to give me the most work. So your work, which will be a little less than the most work, right, divided by the most work, will be a number a little less than 1, right, 0.9, 0.95. In fact, modern turbines can get around 0.95 isentropic efficiency. Okay, that's good. Compressor is the opposite, though, because your work is going to be greater than the isentropic compressor work. Because with a compressor, you're having to put work in, right? And so a perfect compressor will require less work in than an actual compressor, okay? So that's why the actual compressor work required is greater than the isentropic, and we would do the division that way. Isentropic divided by the actual, okay? And again, you don't have to memorize this stuff. But the pumps, again, we're assuming pumps are with liquids. And so we make the second substitution here of the specific volume times P2 minus P1. Now, before I get into this, let me go back to the turbine equation here. And let's talk about what this means, because you haven't seen this before. I want to identify this little thing right here. H2S. What does that mean? See, what you have is you have real state 1 and real state 2, right? You have the two real states. But what is H2S? Okay? What H2S is assuming S1 equals S2. So what you do is you assume S1 equals S2, and then you use that to develop H2S. Okay? That's kind of like your assumption. Constant entropy, you use it to find H2S, and then you have the ratio of that to the actual H1 minus H2. We would assume H1 minus H2S to be a greater number than H1 minus H2. Okay? So H2S will be less than H2, typically. Okay? But that's what you do. In order to get H2S, you connect it to H1 by saying S1 equals S2. Right? And the same thing for compressors. For pumps, you can just use that more simplistic equation that H2S minus H1 is V times P2 minus P1, specific line P2 minus P1, and divided by the actual pump work required. And then the last one I've got there is nozzles, and we assume that the inlet velocity is small, negligible, 0, right? And if that's the case, then you have that equation there for the isentropic efficiency of a nozzle, okay? I will give you several homeworks on this, okay? And I wouldn't be surprised if this came up on the test, okay, of doing something like a homework, okay? Now, the example problem I have today is a little bit different than the homework I'm going to give you, but honestly, the homework I'm going to give you is easier, I think, than this example problem, okay? So let's take a look at the example problem I have here, okay? Now, one caveat on this example problem, I forgot to add a piece of information here, so as we read this, I'm going to have to add a piece of information that I forgot to give you on this particular problem. Okay, so here's our example here. Air enters an adiabatic compressor, so let me draw a compressor here. Okay. At 100 kPa, P1, and 17 degrees C, which, by the way, is 290 K, right? But there's a piece of information we forgot to add, so I'm going to add it in here. At a rate of 2.4 meters cubed per second. This is a volume flow rate. It comes in at 2.4 meters cubed per second. So I forgot to add that in this problem, so add it in yourself. Sorry. Okay? The air exits at 257 degrees Celsius, which is how much Kelvin? What is that? Plus another 140 Kelvin. Plus another 240 Kelvin. So what's that? 530? Yep. 530 K. Okay, 530 K. Okay, all right. The compressor has an isentropic efficiency of 84%, which is 0.84, okay? And you've got your isentropic efficiency equation. So if I see that, if I see an isentropic efficiency, I'm going to go to my isentropic efficiency equation for my compressor, and I'm going to see, oh, okay, that says H2S minus H1 divided by H2 minus H1. Okay, got it? All right. So then here's what we got. I'm going to get two things. I want to get the exit pressure of the air, so that's P2. Okay? And I got to get the power required, required to drive the compressor. Okay? Now, you only have the exit temperature. Right? You only have the exit temperature of 530 K, right? So you don't really have the exit pressure. You do have the inlet pressure, 100 kPa, right? Okay? So what you've got to do is you've got to go back to some of your equations here, and you got to go, okay, what do I got here? I don't have anything here, okay? If you go back to your equations from the previous lecture that I just did, okay? You've got a lot of things there. Now, they're going to assume isentropic ideal gas. You don't exactly have that process here, but here's the deal. What you have is you have H2S minus H1 divided by H2 minus H1 equals 0.84. I could use this to get H2S, right? Okay. Now you might say, how do I get H2S? I have to have H1 and H2. Well, let me show you how to get H1 and H2. How do you get H1? If I tell you I have air, and I have air at 290 Kelvin, how do I get its entropy? Sorry, not its enthalpy. How do I get its enthalpy? You can't get, well, yeah, I could get H2 minus H1 that way, using C sub P, but I got even an easier way. Air for H's, right? Remember? I got tables, right? So that's the easiest thing. What do I always have tables for? I got tables for air, but the problem with air is I can't use it for pressures and volumes. But I do always have H's. If I have air, I can always get my H if I have temperature. So, okay, good. So I got the temperature, and my temperature here was 290, right? So, oh, look, I got it right here. My H is 290.16. Okay, got that. All right. Okay. Oh, and by the way, if I need to get H2, it is at 530 Kelvin, right? I can get that from the tables as well, right? Because all I need to know is the temperature. So I go back to my tables for 530 Kelvin, H2. Oh, there it is, 533.98. 533.98. And those are both in kilojoules per kilogram. Okay. So now that I have H1 and H2, it looks like it'd be pretty simple for me to substitute it into that equation, right? And solve for H2S. That's not a big deal, right? I think we can do that. Let's do it. It's not that hard, okay? So, and you might say, well, how am I going to use H2S? I'll show you here. This is a little more complicated than what you're going to be doing in your homework, by the way, okay? But let's do it. 0.84 is equal to H2S minus H1, which is 290.16, divided by H2 minus H1 is 533.98 minus 290.16, right? And so now use that to solve for H2S. And somebody do that. $494. Basically $495. Yeah. Let's go with it. 495 kilojoules per kilogram. Okay. Can somebody get for me what T2S would be? That would be the temperature of air if H2S was 495. What would be the temperature then? Go back to your tables, right? What do you want to go with the number here? If what's 495 going to correspond to here? If what's what do you think? No, I think you got it the wrong way. 495, the temperature would actually be closer to 490, right? Wouldn't it be a lot closer to 490? Wouldn't it be like 492, maybe? 493? Or maybe 493 would give you a, which give you about a 495, right? Right? They're pretty close, basically. Okay. So basically what I'm saying is that T2S would probably be somewhere around 492K-ish, okay, whatever. It's almost the same value, right? H's and T's are almost the same value. Okay, but here's the deal. I want to get P2. I know P1, okay? So I've got a few relationships there. One of which I've got is this one. P2 over P1 is equal to PR2 over PR1. Now this assumes an isentropic process, but I have a temperature from an isentropic process. T2S is from an isentropic process. So what I can do here is I can use this T2S to then pick up what is PR2. What is PR2? And that same line, let's go back to that same table and say, what would be my PR2? Remember, P's are the first thing. It's somewhere between this number and this number. What do you want to say? You want to go with 8 maybe? Let's go with 8, because it's going to be pretty darn close to 8. Okay? So we'll go with 8. So PR2 is pretty darn close to 8. Remember, there's no units. Okay? Could I get PR1? Can I get PR1? That would be based upon the initial temperature of this stuff. Can I get PR1 based upon the initial temperature? What's the initial temperature? 290, right? Could I use that to get PR1? Sure, right? That's no big deal. Yeah, of course. What is PR1? Look, it's 1.2311 if you want to get technical. 1.2311. So it's about 1.23. Okay? So what you could do is solve for P2 this way. You got that equation in blue. I'm going to manipulate it. P2 is equal to PR2 over PR1 times P1. So that's going to be equal to 8 divided by 1.23 times my initial pressure, which is 100 kPa, right? So it's going to be around 600 kPa, 650, something like that. Yeah, so about 650 kPa. Okay? Now, if you're really paying attention here, you might say, well, hold on a second here. Is the real process an isentropic process? The real process here that has 17 degrees Celsius and gives me a temperature of 257, is that isentropic or not? No, right? It was 84%. It wasn't all isentropic, right? But yet, I used the assumption, see this equation right here assumes an isentropic process. Oh, by the way, I did use the PR2 from an isentropic process, right? So that's kind of good. But yet, I'm predicting the actual. It's going to be a little off, but frankly, I don't have another way of doing it. Okay? So, or, one other way I could do it, by the way, and you will get a similar answer, is instead to do this. You could use those other equations I gave you, which was this. T2 over T1 equals P2 over P1 K minus 1 over K. You could use that, and you will get a pretty close answer with that. But again, you're assuming an isentropic process when you don't even have one. Okay? This problem is a little bit more complicated than I wanted it to be. The problems that I give you in your homework and that will come up in the test, I'm probably going to apply more to turbines and nozzles and things like that, which are going to be, I think, will be a little easier than this one. Okay? Now, the second part of this is actually not hard. The second part of this problem is actually quite a bit easier. Part B. Okay? You can definitely do the second. You should be able to do the second part. Second part says, give me the power required. Well, the power required, okay, work required is going to be m dot times H1 minus H2, okay? Oh, sorry, it's actually 2 minus 1. I don't know what I was saying.
W dot?
Yes, W dot, you're right. And this is H2 minus H1. That's what I meant to say. Okay? Now, you already got your H's. You already got your H's, right? Got your H's here. H2 is 533.98, and H1 is 290.16. So you already got this. You got m dot times H2, 533.98 minus 290.16. Okay, and that's kilojoules per kilogram. So all this does is says, give me m dot. Any ideas how I'm going to get the mass flow through this compressor?
Well, volume flow rate.
Volume flow rate, that's got to be something, right? Yeah? Yeah, yeah. So let's do this. Yeah, exactly. M dot is equal to the volume flow rate, which I'm going to call V dot, times the density, which, by the way, you can also say is the volume flow rate divided by the specific volume, if you like that. How am I going to get the specific volume of air? The volume flow rate, by the way, is what's coming in. You can't say the same volume coming in is the same volume going out. That doesn't work. You can say the same mass going in is the same mass going out. So I'm going to get the volume. What do we always do with air? Yeah, exactly. Okay. If we're in air, you always say ideal gas. If you're sleeping one day and I were to call on you, and I don't do that because I don't, but maybe I should. But if I were to call on you and it's an air problem, reflexively just say ideal gas. I don't know. I was sleeping. Just say ideal gas. But make sure it's an air problem. You could say, is this an air problem? Ideal gas. If it's a steam problem, tables. Yeah. But let's do that, okay? Ideal gas. Remember, ideal gas says PV equals RT. So I want to solve for V. It's V is equal to RT over P, right? R is going to be 0.287. The temperature input is going to be what? 290 K. And this is going to be 100 kPa, right? I believe that's it. So it's 0.287 times 290 divided by 100. What's that number? Point what? 0.83. Good. And the units on that are going to be meters cubed per kilogram. So you're going to have 0.83 meters cubed per kilogram as your specific volume. Your actual volume flow rate is 2.4 meters cubed per second. Therefore, the mass flow rate is what? Just 2.4 divided by 0.83. That's not too bad. 2.88? Okay. 2.88 kilograms per second. Oh, well, then the only other thing you got to do now is take that m dot, throw it right in there, and you'll get our work required. This is the work it takes to power this compressor. Yes. Well, it's actually a real compressor because it's the real one, not an isentropic. It has an isentropic efficiency of 0.84. I think it's like around 700. 702, and if you work this out, that'll be kilowatts. Because kilojoules per kilogram times kilogram per second, it's going to be kilojoules per second. That's kilowatts. Cool.